Hey there, math fans. I want to talk about vector projection. It's an important application of dot products, but it's also just fun. So this is going to be more of the fun video. I'll probably follow up with a more technical one for my students here in a second. It's these formulas. I find students are very confused by these formulas because partially just the naming of it, the fact that the word projection appears makes it sound scary, but it's extremely valuable. So I'll just start with a quick visual here. Here are my cats sitting on a wagon. Here's Harry the husky about to pull them. Let's pretend that he's pulling with about 50 pounds of force. And we ignore if these numbers don't make any sense. I'm just giving an example. And imagine he's pulling them up a ramp. For this situation, I chose the ramp to be 30 degrees. And I also have Harry pulling at another 30 degrees. So it's a total of 60 degrees there. What happens in these physics problems is you often want to know how much force is the direction you're going. That's a projection problem. These happen all the time. I'm going to show you a bunch of cool visuals here in just a second. If you can find two vectors, we have a very clean, nice, short formula here that follows directly from this. But again, I'll do that in a separate video, that technical piece. It says you just have to do their dot product of some vector that represents the ground and a vector that represents the pulling, and you're all set. Meaning I need some vector that represents that ground, let's call it U, and I need some vector that represents the pulling on this rope, let's call it V. If I can find those, I'll be immediately done. Okay, so a vector that goes up 30 degrees, you have to know your unit circle to do this problem, which a lot of students don't, but if you want me to post a separate video on that, I can. But this is square root of 3 over 2. This is 1/2. So I need some vector that has that. So you could use square root of 3 over 2 and 1/2. A lot of times in physics, they use a unit vector, which that is. But you could also rescale it and use this vector. So that's the vector that represents the ground. It turns out it doesn't matter. You even multiply that vector times 1,000, and it still would work. We'll talk about that in a second. But now I'd like a vector that's here. Now this in total is 60 degrees, so we need another point on the unit circle. 1/2 comma square root of 3 over 2. But this time I'm going to multiply by 50. Okay, we really think of that as the force in most applications. So we've got this force. The force that he's pulling with is 50 times that. So it's 50 times 1/2 is 25, and then 25 root 3. That's the force, but I want the force to be in this direction. That's what we're doing. And it says all you have to do is take the dot product and divide by the length of the thing you're projecting onto. So we're going to multiply. Let's do it with this vector first. We're going to multiply those two things. So we get 25 root 3 plus 25 root 3, because we did that times that. So it's 50 root 3 divided by the length of the thing we're projecting onto, which is the square root of 3 squared is 3 plus 1. Done. It's really that fast. So it's going to have 50 square root of 3 over 2, or 25 square root of 3. And I didn't compute that ahead of time. I'm doing this on the fly here. So we have 25 times square root of 3, 43 pounds. And what's nice in these questions is you can see that that's maybe reasonable. 43.3 pounds of force in the direction we're going. That's useful because if you want to actually model the motion of the wagon, that's the number you need to know. It might be also nice to have a vector in that direction, but that's fairly easy to get because you want to take this vector and rescale it to this length, and we already talked about that when we did rescaling in my course. How do you rescale? You take whichever vector you want to rescale, you make it a unit vector, and then you multiply times the desired number. In this case, it would be this. But in general, it's going to be whatever this is. So I don't even memorize the projection formula. Projection formula is the thing you get when you rescale your vector to this length. That is it. If we just projected onto this vector, we would have gotten the exact same final answer. You can try that out and see. Okay, my kid said I had to animate this, so here we go. Let's have him pull my cat's up. Let's make it a little bigger. just for a moment, and then I'll show you a couple other visuals. Here we go. And they said that I had to make them fall off. Okay, that was fun. Oh, they got back up. Great. Some other visuals I thought would be sort of fun to see, just to give you a sense of why I think this is really important. Every time I wasn't a physics major. I didn't do a lot of things with physics, but every time I encounter a physics problem with forces in motion, I'm always doing projections. The fact that I know a little bit of math helps me. So I was thinking of another situation. Here's, let's get this back over here. Apologies as I adjust a little bit. Hope this is interesting. Hope someone's listening. Okay, here we go. Here I have the ships from Battleship here. And they're about to cross a river. Here's the river going by. But I'm going to visualize the river as if it's a bunch of vectors, and that's the velocity of the river going by. We do this a lot in our first course where we do this is Math 224, but those could represent forces, they could represent velocities, and we want to measure something. So I'm going to take the smallest ship, and we're going to go across the river. This is a fun little exercise. It's going to follow that path. And I use tangent vectors so that I could draw it. Here it goes. There goes our boat. I even got it to turn. Look at that. Following that path. Now in that course, they have to talk about parameterizing a curve so that they can measure this. But at any point along the way, as it's going, we can ask various questions. So here it goes again. So at a given moment, we can say, well, what is the tangent direction? And if I gave you the curves, you could find that. But that's not the direction that the river is going. The river is going this way. And so we usually call this R prime. And we'll talk about that in chapter 13. And we call this either the force or the velocity at that point. And what happens is you have this vector, x prime, y prime, and you have this vector, which is the force at that location, AB. And what we usually are trying to measure is how does the force help us or does it hurt us? And that's a projection question. And so when I taught this Math 224, I had to think about this a lot, again, because I don't come from a physics background, but I learned a lot. So we have a force this way, we have the object traveling this way, and you don't need to know any of this for Math 126, but I thought it would be interesting for me to talk about. How much of in this case, the force is helping us a little bit. The river's helping us a little bit, but how much? It's a projection. And so often what happens is you'll see this, F dot R prime. And if you want it to be the projection, you do this. Sometimes we wait to rescale. Sometimes we say it has to be a unit vector, but that's what you get. If you want to add up all those projections, we have this fancy notation that says the integral over the curve of f dot dr. And f dot dr means we're going to measure the projections relative to the tangent vectors. Sometimes we measure the projections relative to the normal vectors, like if you submerge a net and you want to measure how much flow is across this net per hour, then you might measure it relative to the normal vectors. Sometimes we say we measure it to the unit tangent. I think there's all different sorts of notations. There's like a dt, there's an f dot dn. I don't know that it's even written that way. I might be using it wrong. Again, that's not my area of expertise. But every time you see this, it's a projection. If you add those up, it's like the effort. A lot of times this is like the work necessary, the work done by the river on the boat or the boat on the river. I always have to remember how to say that correctly. But it was fun making that little visual. I hope you found that sort of interesting. This extends to higher dimensions. So I got one more for us. This is from our textbook. I think I got this from our textbook. Something. I did not make this. This is when we're trying to measure something flowing across a surface. Sometimes they do this in a course on, electrodynamics or some things I don't know anything about, but I understand what they're trying to measure. They call this an upward pointing normal for the surface, and the surface has different upward pointing normals, and they might be trying to say, hey, there's a force this way, and I would like to measure how much of the force is going straight out of the surface. F dot N. Now, usually it's just F dot N because they choose this to be a unit vector. That'll be like part of the statement of the problem. But technically, this is the projection. It's just if that's a unit vector, that's 1, and it makes things simpler. So this is something I've always meant to make. I don't do all that in class because it just takes too long. Interesting other things. This is from the last time I taught Math 324, which is now 224. I have a bunch of review sheets on things like this, how you have to parameterize the surfaces, what it means to be a conservative vector field. And some interesting things pop up in this discussion. For example, if I move my hand around in space and make a loop, sometimes gravity is working with me, sometimes it's working against me. We say that gravity is a conservative vector field, and if I move my hand in a loop, the total work done is 0. I feel like I did some work. But they defined it to be positive when it's with us, negative when it's against us, and they cancel things out. That's called a conservative vector field. Not everything's a conservative vector field. There's certain properties of that. So that's the sort of things they study in physics and engineering. But this ultimately is what we're doing. That was just to give a little bit of interest. But what we're trying to just figure out is how long that is. And I hope I've given you several examples of why we might want to see that. And I'll probably follow up with some computations just so you can see it in action. But I thought this one was pretty good. So there you go. Oh no, don't pull them over. All right. Thanks for watching.